right, guys, welcome to our first lesson of week number 3. Today we're actually going to start stoichiometry, and this is going to continue for the rest of our course, whether we're online or in person, and it's a significant part that you need to know for grade 12 as well. So what is stoichiometry? It is the study of quantitative, okay, so the actual amounts, the values, so it's the relationships among amounts of reactants and products in chemical reactions. We've already started this without calling it stoichiometry by looking at moles, all right? So learning how to put quantities of chemicals into amounts that are easily compared. And that's why we have the mole as well. Because when we look at molar mass, we see that the mass of one chemical doesn't necessarily correspond to an equal mass of the other because the molecules or formula units are different sizes. So one thing we have to remember in stoichiometry is the law of conservation of mass. So don't forget that the mass of the reactants is equal to the mass of the products. And if we break this down further, it's that there is no loss, not just of mass, but of particles. So the number of particles involved in the reactant side will be equal to the total number of particles on the product side. For example, where are we going to see this come into play? Let's have a reaction here. If we look at burning solid magnesium in oxygen gas, and it forms solid magnesium oxide, the law of conservation of mass is why we have to balance this. So I would have 2 magnesium plus oxygen forms 2 magnesium oxide. And these coefficients are representing the relative amount or number of particles. Remember that particles is a catch-all term for atoms or formula units or molecules. So this is giving us a relative comparison. By using these coefficients, we see that 2 atoms of magnesium react with 1 molecule of O2 to produce 2 formula units of magnesium oxide. We can simplify this more, and it's what we're going to call a mole to mole ratio. So if we look at the number of moles of magnesium reacting with the number of moles of oxygen to produce the number of moles of magnesium oxide, that means we have 2 to 1 to 2. That says that 2 moles of magnesium react with 1 mole of oxygen to produce 2 moles of magnesium oxide. We're not even bringing mass into account right now. We're looking at mole to mole ratio. We can go backwards with mass and see what mass 2 moles of magnesium would have, what mass of oxygen that is, and we would see that would equal the mass of 2 moles of magnesium oxide, but I want us focusing on this mole to mole ratio. Let's try another example. If I told you that nitrogen gas reacts with hydrogen gas to produce ammonia, I want you to press pause right now and write out a balanced chemical reaction for this. Two, 3. There's my balanced chemical reaction. Underneath it, write out the mole-to-mole ratio. So press pause and write the mole-to-mole ratio here. We see that it's 1 to 3 to 2. So what I'd like to know is how many molecules of nitrogen gas are required to produce 10 molecules of ammonia. Well, I'm going to set up our proportion here. So I'm going to say my nitrogen gas to ammonia. Well, it is a 1 to 2 ratio. So 1 molecule of nitrogen gas will end up producing 2 molecules of ammonia. Okay, I have X molecules of nitrogen gas, and I want 10 molecules of ammonia. So you're just going to solve for X. Here I can cross multiply. 1 times 10 is 10. Divided by 2 is 5. I get X equals 5. So 5 molecules of nitrogen gas will produce 10 molecules of ammonia. Let's continue with the same reaction, and you're going to tell me how many molecules of hydrogen are required. Press pause and figure this out for me, please. So I'm going to refer, so keep nitrogen gas and compare it to hydrogen gas. I could use ammonia and hydrogen gas. It doesn't matter. I have the ratio and amounts for both of them. That's going to be my mole-to-mole ratio or molecule-to-molecule ratio is 1 molecule of nitrogen gas is reacting with 3 molecules of hydrogen gas. If I have 5 molecules of nitrogen gas, how many molecules of hydrogen gas do I need? Do your cross multiplying, and we find that X equals 15 molecules. We see that 15 molecules of hydrogen gas are required. Okay, let's try another one. For example, how many formula units of calcium chloride are produced by 6.7 times 10 to the power of 23 molecules of hydrochloric acid that reacts with excess calcium hydroxide? Now, why did I put this term excess in? That means we have much more than required. So we don't need to worry about this amount. That'll come into play more next week. So again, press pause, write out a chemical reaction for me, please. Make sure you balance it. Here's the reaction you should have come up with. We've got hydrochloric acid. It's an acid, so it's aqueous. It's reacting with calcium hydroxide. That's solid. Okay, now we didn't really get into double displacement reactions because of, the COVID shutdown. That's something that we eliminated from the course for this semester. But you did do double displacement reactions in grade 10. This is a neutralization, so remember we're just going to switch our anions. All right, so we're going to end up with calcium chloride, which is aqueous, and water as a liquid. Sorry, that's hard to see there. And once I balance it out, I'll get 2 and 2. That means my mole-to-mole ratio is 2 to 1 to 1 to 2. And if I'm going to compare here calcium chloride and hydrochloric acid, well, HCl to calcium chloride is 2 to 1. So now, if I have 6.7 times 10 to the power of 23 molecules of hydrochloric acid, figure out how many formula units of calcium chloride that will produce. When I solve for x, I'm going to use my calculator right here. That's going to give me 3.4 times 10 to the power of 23 formula units of calcium chloride produced. Great, let's keep going. New example. Please calculate the amount, we're going to switch to moles this time, of oxygen gas that's needed to react with 3.4 moles of propane in a complete combustion reaction. Press pause, write out this combustion reaction for me. Okay, so remembering that complete combustion, we have our hydrocarbon burning in oxygen to produce carbon dioxide gas and water vapor. Combustion is hot, so we're not going to have liquid water after. Balancing it out, we're going to have 3 carbon dioxide, 4 waters, and 5 oxygen. So underneath here, I'm just going to start by writing out my mole-to-mole ratio. That'll be 1 to 5 to 3 to 4. Now, if my number of moles of propane is 3.4 moles, then I need to know X number of oxygen moles. And you know what? Challenge yourself, guys. Figure out the moles of the products as well. If I had propane to oxygen, that is a 1 to 5 ratio. So I can solve for X. I'm going to get X equaling 17 moles. I can also compare this to carbon dioxide. So if I did propane to carbon dioxide, that's 1 to 3. Y would be Okay, Y is going to give me 10.2 moles, but I need to look at sig digs here. Okay, I've only got 2 sig digs, so I'm actually going to have to rewrite this as 1.0 times 10 to the 1 mole. There's 2 sig digs. And finally for Z, for water, C3H8, the water is a 1 to 4 ratio. And that's going to give me 14 moles. We're going to keep going with another example. Press pause if you need this. Last one. Find all amounts of the reactants and products when 1.75 moles of copper react with nitric acid. When I write out this chemical reaction, I'm going to have solid copper reacting with nitric acid. Now this is a single displacement reaction. So thinking again in grade 10, we did cover this. Single displacement, copper and hydrogen are going to swap places. Sorry, I'm just looking at my note. Okay. Let me write this lower where we have more space. We got copper plus nitric acid gives us copper nitrate, copper 2 nitrate, so why is this reaction? What's going to happen is this is going to partially dissociate, all right, to break down into nitrogen monoxide and water. I'm giving you this chemical formula. So balance that out for me. Press pause. This one takes a bit of work. You end up with 3, 8, 3, 2, and 4. Wowza! Right now, let's write our mole-to-mole ratios underneath. I'm going to start keeping this as a chart. It's not totally necessary just for this problem, but moving forward through the rest of this week and into next and, the rest of the course, we are going to want some organization, so it's a good practice to start now. So our mole-to-mole ratios, 3, 8, 3, 2, and 4. What are the actual amounts that we have? Okay, we're starting with 1.75 moles of copper. So I can now calculate all of these missing values using a mole-to-mole ratio. So if I say copper to nitric acid, well, that would be 3 over 8 equals 1.75 over X moles. And I'm going to find that that gives me 4.67 moles. Repeat for the next 3, please. Here I could say, hey, 3 to 3. 3 over 3, well, that's 1 over 1. So 1.75 moles of copper will produce how many moles of copper 2 nitrate? It's going to be the same, 1.75 moles. Nitrogen monoxide, 3 over 2 is our ratio. So 1.75 moles of copper will produce how many moles of nitrogen monoxide? Do your math, and you get 1.17 moles. Watching sig digs all the time. And finally, 3 to 4 is 1.75 moles over what? We'll get 2.33 moles. So that's how we're going to use mole-to-mole ratios comparing chemical reactions. Make sure you try all of your textbook questions that you're looking at. It looks like a lot, but practice, practice, practice. And then when you're ready, come on back and we'll look at including some math in this. Thanks a lot, and I hope you have a great day.